Hello, my name is Orlando and this is about projectile motion. Here you can see that the force equation is equal to F equals to negative mgj. The component is j and the sign is negative because the force of gravity acts vertically downwards. Now as we set the force of gravity equal to Newton's second law, we can cancel out the m and are left with A equals to negative gj. Okay, so moving on to example 5. It essentially asks us for the position function of a projectile. To get the position function, we need to first integrate the acceleration vector to get the velocity vector. So here we use the acceleration function, which is equal to negative gj, and then we set the integral of that to the velocity function. So we integrate this, and we are going to get negative gtj plus c sub 1, which stands for constant number 1. Now we will plug in for when t is equal to 0. So we get v of 0 is equal to negative g times 0, which is essentially 0, plus c sub 1. So what this gives us is that c sub 1 is equal to v of 0, which is also equal to v naught, which is the initial velocity. Now we will integrate the velocity function we just found. Now with v naught replacing c sub 1. We set the integral of the velocity function to r of t, which is the position function. That means we will be taking the integral of negative gtj plus v naught dt. As a result of integrating the velocity function, we get negative 1/2 gt squared j plus v naught t plus c sub 2, which is the second constant we get from integration. Now, to solve for c sub 2, we can set t equal to 0 and solve for the position function. So here we plug in 0 for t, so we get negative 1/2 g times 0 squared j plus v naught times 0 plus c sub 2. So here we get r of 0 equal to c sub 2, which is the same thing as r naught, which is the initial position. So our final position function or vector will be negative 1/2 gt squared j plus v naught t plus r naught. And this is a solution, and we did manage to get the correct answer. So basically, to get to here, we draw a right triangle with the initial velocity at the hypotenuse, and we can use trigonometry to relate x or y with the angle and the initial velocity, and we can isolate x and y to get y is equal to initial velocity sine theta and x is equal to initial velocity cosine theta. We can back substitute it in to get this equation. If we remember, this was the position vector. So the question is, how do we end up with this final equation again? Well, it's actually pretty simple. So basically, here we have V naught already, right? So we can actually plug V naught into this position vector. So we will get R of t is equal to negative 1/2 gt squared j plus t, and then in here it would be V naught cosine theta I plus, right down here, V naught sine theta j plus R naught, which is initial height, can just be h, and the component will be j because height is in the y direction. So here, this is t. So here we can distribute this out. We could get negative 1/2 gt squared j plus t v naught cosine theta I plus t v naught sine theta j plus hj. Now we can separate the I component and the j component. Here we get t v naught cosine, not sine, cosine. That's a bit messy. Cosine theta I plus, there's three terms with j, so negative 1/2 gt squared. So we have this term, we have this term, plus t v naught sine theta. We got this term plus h j, and that will be our new position function vector, which is, yeah, it's basically exact same thing as this, just the terms are ordered differently. Yep. Okay, so now that we have our position function here broken down into its horizontal and vertical components, it will make solving problems such as here example 6 on 2D projectile motions much easier. So let's read example 6. A baseball is hit 3 feet above ground level at 100 feet per second and at an angle of 45 degrees. So hit at 3 feet above ground level, so h will equal to 3. That's the initial height. Ground level 100 feet per second. So the initial velocity is equal to 100 feet per second, and height is 3 feet. At an angle of 45 degrees, so theta will equal to 45 degrees. 45 degrees with respect to ground, as shown in figure 12.8. We can just draw the figure. So find the maximum height reached by the baseball, and will it clear a 10-foot high fence located 300 feet from home plate? So this question is actually asking for two parts. So maximum height here, and will it clear a 10-foot high fence 300 feet away? So let's draw the diagram. So it should look something like this, where this is V initial, and then something like this, right triangle, and this is 45 degrees, and this is 3 feet. So the first step to solving this is probably just to plug things into this position function and see where it takes us. So we can do r of t equals to v naught is 100, cosine of 45 degrees is, we know that is root 2 over 2 t I plus height, which is given, is 3 feet, plus here v naught is 100. Sine of 45 degrees is same as cosine of 45 degrees, which is root 2 over 2 times t minus 1 half g, pretty sure it's 32 feet per second, so it's like that, j. We can simplify this a bit, so we will get r of t is equal to 50 root 2 t I plus 3 plus 50 root 2 t minus 16 t squared j. So how do we find when the baseball reaches the maximum height? To answer that, we have to work with the y component of the position function. So the y component position function, we can say that is y of t is equal to 3 plus 50 root 2 t minus 16 t squared. So now if we think about a projectile moving, projectile is going like this. When it's at the very top, one unique thing is that the derivative will equal to 0. This will be y prime of t. Like here, y prime of t will be positive. Here, y prime of t will be negative. But when the baseball is at its maximum height, y prime of t will equal to 0. Now this becomes pretty easy. We just have to take the derivative of y of t, which should be 50 root 2 minus 32t, and you set that equal to 0. Now we just have to isolate for t. We get t is equal to 50 root 2 over 32, and we can simplify that to 25 root 2 over 16. So we get that when the baseball reaches its maximum height, this much time has elapsed. So we can actually back substitute t into its y component to find the height, the maximum height. We do y of 25 root 2 over 16 equals to 3 plus 50 root 2, 25 root 2 over 16 minus 16 25 over root 2 divided by 16 squared. And if you do calculate all that, you will get 649 over 8, which is around 81 feet. So the baseball reaches a maximum height of about 81 feet. So now for the second part. The second part asks for whether or not it will clear a 10-foot high fence located 300 feet away from when the baseball was hit. So how do we solve for this problem? So this problem is pretty simple. So basically we know that the distance will be 300. So we can actually set the x component here. X component, if you bring it down, it will be 50 root 2t is equal to x of t, and the distance will be 300. So we can solve for t. We get t is equal to t is equal to 6 over root 2, and then we can rationalize this. You could get 6 root 2 over 2, which is 3 root 2 seconds. So when the ball reaches 300 feet horizontally, we know that 3 root 2 seconds has passed. So now what we can do is plug in 3 root 2 seconds into the y component to find the height of the projectile when it is 300 feet out in the horizontal direction. So here we can do y of, this is the time, 3 root 2 equal to, so it was 3 plus 50 root 2 times the time, which is 3 root 2, minus 16 times 3 root 2 squared. So what I get will be equal to, so this will 3 plus 100 times 150 times 2, 300 minus 16 times 18. Yeah. 3 root 2 is equal to 3 minus 288. So this means the height of the baseball at 3 root 2 seconds, which is when the ball is 300 feet out, will be 15 feet. So since the ball is at 15 feet when it reaches the fence, it will clear the 10 feet fence. So yes, it will clear. And thank you.